What is going on, guys? We're back playing some more Surviving with Mekanism version 10, and today we're going to be going over the water-cooled fusion reactor. Now, last episode we set up the air-cooled fusion reactor that is running right in front of us right now, and it's been running for quite some time now at a relatively low injection rate, and it's been generating tons of power, far more than anything else we've set up in this entire series, even though it's almost as low as you can possibly set it, and the air cooling is the most basic version. So today we're going to be kicking it up another notch to get even more power from this by upgrading it from air cooling to water cooling, which is going to make it passively generate power and produce steam, which we're then going to input into an industrial turbine to get even more power. So if you're playing in a mod pack and you're looking to max this thing out, then making it go from air cooling to water cooling is going to be your best bet to get even more power from it. Now, thankfully, it's relatively easy to upgrade to, probably one of the easiest upgrades we've done so far in this series. And so today we're actually not going to be reassembling an entire fusion reactor from scratch and then making it water cooled and having two of them running. We're actually just going to go from where we left off last episode and upgrade the base air cooled version, since like I said, it's very easy to do. And so if you have not set up an air cooled fusion reactor and you don't know how to do that, then I'm going to put a card up at the top of the video right now, and I would highly advise you to go watch that episode, learn all the basics about how the fusion reactor actually runs, how to set it up, how to start it, all that good stuff, then hop back here and you can upgrade it even further. But it just didn't make any sense to me to do a second one with how expensive the material is to make it and all that stuff, and because we just went over it a couple days ago. So hopefully you guys are okay with that. But to upgrade this, we're actually not going to have to do any crafting. So hopefully that makes up for it, because nobody likes watching the crafting portion of the videos. But we only really need two fusion reactor ports. One is going to be a new input, one's going to be a new output, and that's it. Now over here we do have a couple electric pumps and some upgrades and whatnot. That is just for inputting the initial water requirements. If you're playing in a mod pack or you have other options, you can feel free to use those. They're probably a lot faster than this, but these should do the trick for us because we're just going to get an initial amount of water in there, and then we're going to be making a closed loop system that should run at steady state conditions with this industrial turbine back here, and we're going to go over all the numbers you need to know to actually get that set up later on in the video. So the first thing that we need to look at when we are going to set this up is going to be the controller right at the top, and we're going to go to our injection rate on the fuel tab. Now we have it at a 6, the lowest you can set it at is a 2, but you're going to want to figure out what injection rate you want to have this running pretty consistently at before you actually start setting this stuff up, because the sizing of the industrial turbine, unless you plan on making the biggest one possible, is going to be determined by the injection rate, because the injection rate is going to affect the stats tab, which if we go to that, you will see you have all this information. The only two important pieces are the passive generation and the steam production. Now you can see with the air cooling that we have passive generation right now of 3 megajoules per tick. But if we go to the water cooled at the bottom, we have passive generation of 750 kilojoules per tick and a steam production of 900,000 millibuckets per tick. So what this means is that even while you're producing steam and doing water cooling, instead of just producing steam, you will still produce some power, which is awesome, but you are going to have to process all of that steam that you're producing to get the most bang for your buck out of this. And you're going to do that in the industrial turbine. And so we need to know the amount of steam that we will be producing, which is going to vary with your injection rate. So if this varies a ton after you've set up your industrial turbine, you might run into a situation where your turbine or your setup in general is not able to either process or move the steam and the water back and forth at a rate that's needed to keep this thing water cooled. So that's why it's important to figure out what you want to run it at. I'm going to leave it at 6 for now. There's not a huge need for a ton of power since we're only playing with Mekanism right now. So this is just going to be an example, but if you want to run it really high, you're going to want to make sure you have it running at that and know the steam production before you actually set this up. But so for us, I'm actually going to be running it at 4 consistently. And if we look at that, that's going to give us 500 kilojoules per tick of passive generation, which is a little bit lower than the passive generation of air cooled at 2 megajoules per tick, but the steam production once we process it will more than make up for that. So we want to remember this number, 600,000 millibuckets per tick. And what we're going to do now is come down and we are going to put the 2 additional ports on. Now this is going to bring us to a total of 5 ports for the entire system, and you're going to have 3 inputs, the deuterium, the tritium, and the new port, which is going to be inputting water. And then you're going to have 2 outputs, the energy output that you already had, and then you're going to have the new output, which is going to be steam. And these ports, much like we talked about before in last episode, can go on any of the faces of this setup. They just cannot go on the edge blocks. So we're going to be putting one on this side over here and then one on the other side. So if we break this and we grab it and then we put down the port, you can see that it actually starts up the reaction again inside, like I said, so you can avoid having to shoot another laser in here, which, like I said, is the most annoying part of actually setting this thing up. It's a relatively small multi-block, but having to get that energy with the lasers and how long it takes, and then you probably set up a ton of lasers and then you just break them, it's a huge hassle. So making sure that this keeps going is a super awesome thing that comes along with just upgrading this very quickly. So we have the 1 input over there, and then we're going to put down another port over here. And so with these, we're going to want to set one of them to input and one to output, and you can do whichever side you want as the input and whichever is the output. We are going to be doing the output on this side. So we're going to shift right click with the configurator and it switches to output. Now these outputs and inputs do not have any specific configuration. Obviously, with some of the different multi-blocks we've worked with, they have specific outputs for steam and water and inputs for the fuel and nuclear waste outputs. These do not specify. So you're just going to have 3 of the regular inputs for deuterium, tritium, and water. And whatever you throw into them is it's going to put it into the proper section regardless. And then the outputs, 1 for energy, which we have back here, and then 1 for steam over here. Now we're going to go to the industrial turbine, which we also already have an episode on, where we go over all the important information about how to set these up. There's a ton of math that goes along with it to figure out how to get the numbers correct. So again, if you do not know how to set these up yet, I would highly advise you go and watch the episode on that. Chances are you probably already know how to do this because you're going to need to have a fission reactor set up to even get to this point. And so you'll probably already have one of these set up to at least deal with a water-cooled fission reactor, if not a sodium-cooled one. So I suspect you're a pro at industrial turbines now. But what we need to make sure is that whatever our steam production is from whatever our injection rate is, that the max flow that is listed here at the bottom of the industrial turbine and the turbine statistics, which list the max water output at the very bottom, we need to make sure that both of those, whichever one is the lowest of the two, is still higher than the steam production currently going on in our fusion reactor. Now, obviously with these, they're almost the exact same. And so that's actually what you'd want. If you're going to get close to the maximum rate that you can process in one of these, having them very close to each other means that you've actually set up the ratios relatively well. And so right here we have almost 5 million millibuckets per tick max flow, and we have almost a max output for water of it's about 4.75 million millibuckets per tick. So it's a little bit lower. So the max water output would be our limiting factor in this, but that is well over the 600,000 millibuckets per tick of steam we'll be producing. Now, the reason this is important is because if you plan on making a closed loop system, you want to make sure that every single drop of steam that you are putting in is being recondensed into water immediately so it can come back out to your system here, and that you do not have a sort of bottleneck at the steam production, because if you do, then your system is going to run into this chain reaction where it's producing steam, but that's not processed quick enough, so it runs out of water and all that stuff. Now, this is not as critical if you are not planning on making a closed loop system, but there's no reason not to, because you're just wasting power if you plan on continuously pumping water into this thing and not taking advantage of the fact that you can completely recycle it using the turbine vents and just condensing it back from steam into water. So we are going to go over, if you saw a couple episodes ago when we set up the sodium-cooled fission reactor, the weird nuances that come along with the way Mekanism actually deals with calculations, and how there will be a requirement for you to put in a little bit of extra water in here so that you do not run into the issue with buffers that will occur. But we will be going over that once we have it set up. But the main idea behind this is you want the math to work out. You want to make sure that this is producing less steam, then this can process both steam and output water. If you have that, you are all set to go with actually hooking these up and starting to pump the water in. So we're going to grab out our pressurized tubes and mechanical pipes. And something that I want to stress is that you want to make sure that you are using piping and tubing that is able to actually move the amount of steam and water you are producing, because that's another potential bottleneck that you could run into. A lot of people don't know, and this is a super weird interaction, but we'll go over it with the pressurized tubes. We'll put these down right here. And of course that connects here when it shouldn't, but it doesn't look like anything's being output from that side, thankfully, because I adjusted it. So here we go. So we have the steam output, and this is going to go to the turbine valve, which is going to be the input for this. So the steam's going to come right through here. Now, with these pressurized tubes, we want to make sure that these are able to transport all the steam we are producing. Now, if we look at the pressurized tubes, you can see that they have individual pump rates and capacities for them, but if we actually look at this tube system, we can multiply those values by however many tubes are connected. Because as you extend a tube system, the rate at which these can move the gases through them is increased by the quantity of tubes that are connected. So if you have a single tube right here, and this it doesn't really make sense to me, but if you have a single tube right here and you connect a second one, the rate at which this tube can move gas through it to this tube is twice as fast because you have a second tube in the system. So right here, because we have 4 tubes, it's 4 times as fast as if we had a single pressurized tube connecting these two together, if they were right up against each other. So a lot of times you might run into a situation where even if a single ultimate pressurized tube is not sufficient, you can extend it a little bit by using a couple extra tubes, and that'll make all the difference with being able to move it quick enough from one to the other. So we're going to run into that same situation over here when we hook up the input, and this is going to be the water input, which we're initially going to have to supply ourselves, but with the industrial turbine, we're able to pull from the turbine vents, and so we are just going to go right here and run this up the side, and there we go. So this should be sufficient to pull back all the water we should be condensing from these turbine vents and the saturating condensers up above the pressure dispersers in there. And now, once we input water into this thing, it should be good to go. And really, the greatest thing about this, guys, and I think we're all going to enjoy this, is that the fusion reactor cannot explode. So even if you are not supplying sufficient water to it, or we started out and it's water cooled for a second and then it runs out of water and it's not, nothing bad is going to happen. So we are able to just freely pump water into this thing until it's at a sufficient point, and we don't have to worry about it overheating or anything like that, which is awesome for trial and error when it comes to actually getting these values right. So the reason I say that is because, again, we have to deal with the internal buffer issues of mechanism calculations. So what we're going to do is put down some pumps right over here. And so we will, well, actually, do you want to put them down right here? Yeah, we can just put them down right here. So we'll do that, and then we'll toss down the quantum entangler right back here. We'll get out our universal cable to run like so. Get some power going here, and then toss down these pumps. We'll put the upgrades in them, and hopefully they will get us a decent amount of water in here. It shouldn't take too long to fill up because we don't have a crazy injection rate, but we're just going to shift click all these in there so it's instant. You guys taught me that in like the first episode. I had no idea they had that functionality in here. And then we're just going to put the mechanical pipes right along the top. So there we go. We are now pumping water in here, and if we could access this from the top and we look at the heating, you can see we have water very slowly coming in here, and you can see that it's actually cooling off the plasma in here, and it's cooling off the casing. Now, the reason that's occurring is because if we look over at the stats tab, the max plasma temp and the max casing temp for the same exact injection rate is going to be way lower for the water cooled version, obviously because it's water cooled. The water is going to allow us to pull more heat away from it, and obviously it's going to use that heat to produce the steam from the water. So you're going to see that it starts dropping off, and this is an important thing to keep in mind because at the beginning of this, chances are your reactor is going to be at a higher temperature and producing actually more steam per tick than it will once it hits its equilibrium point, which is the temperature listed as the max plasma temp. So at 300 megakelvin, this thing is going to produce this many millibuckets per tick of steam, but when it's above that, so right now, it's actually producing more than that. So if you have this set up, you're going to want to make sure your water is sufficient for whatever the actual max temp is, not whatever the temp is that it's currently at, because if you are starting water cooling at the same rate that you were doing it at before, then chances are your plasma and casing are both going to be reducing in temperature for the very beginning of your setup. So you can see this is slowly filling up, and if we come over here, you can see that the flow rate is constantly going up because as we're pumping more water in here, it's got more water to actually send into the system over here. But all we need to make sure is that eventually in here, if we go to the right tab, that the water in here that's sitting in this system is more than the amount that is produced, or more than the steam produced in one single tick. Because you need to make sure, if you want to get the most out of it, that you have more water in here. So we're going to want to make sure we have at least 600,000 millibuckets of water sitting in here at any given time due to how the mechanism calculations work. And over here, once that happens, you'll see that this will start to cap out its flow rate once the temperature equalizes on this reactor over here, which is going to take a while. Obviously, it's still got 120 megakelvin more to drop, but it's going at a pretty steady rate. And if we look over here, look at the production right now. Obviously, the flow rate will continue going up as we get more water in there. Even though the system is cooling down, it doesn't have enough water to produce more than 600,000 millibuckets of steam. So right now we are generating 4.1 megajoules of power, which is way more than, if we look at this, we're kind of hopping back and forth all the time. It's more than twice what the passive generation was for the air-cooled at this same rate. And we are not even at the maxed out point for this. We'll probably be around 3 times the amount of power just from processing the steam, not even including the passive generation of 500 kilojoules per tick that we will be getting from the water cooled. Now, right back here, we have the quantum entanglement receiving power from both of these. So our power system upstairs is probably loving this. And right here, if we keep looking at the heat tab, just to keep an eye on the water, if we keep going up, eventually we're going to hit a point where it actually should be sufficient. But we can quickly go over the reason that you actually need more water pumped in here than just 600,000 millibuckets. And that's because over here, you can see that the steam in here is actually sitting here, even though we are processing it at a sufficient rate. And you can see, side note, we just crossed over the production that we should currently have. So this will eventually drop back down to 600,000 millibuckets, but we will have a certain amount of steam just sitting in here. Oop, yep, it's dropping down now. So if we look at the heat in here, we can see we are nearing the equilibrium temperature. But either way, we are going to have steam sitting in here. That just happens. Even if everything in here is being instantaneously processed, because of how Mekanism does the calculations and the transportation of gases and fluids, it is going to have steam sitting in here that will sit, once this eventually all reaches equilibrium, it will sit at a constant amount. And so that means that everything coming in is instantly being processed. Nothing is coming in and gaining in here. Nothing is going down. So it's actually perfectly being processed. But because of how Mekanism works, there's just going to be a static amount of steam sitting in here. And because of that, we need to pump in an excess amount of water into the system so that it can actually function, even if it mathematically should be totally fine. So here we go. We can see that we now have this completely full of water. We can totally disconnect these right here and make our base look nice and pretty again. And the system will be able to function completely on its own without us having to touch anything. So let's get back out that smooth stone so I can fill in the floor here. And if we come and take a look at this and we go in here, you can see that the water is sitting at a consistent amount. The temperature is going to go a little bit below what it says it should be for the max plasma temp. And then if we go in here, you can see that eventually it will stabilize both in the internal steam and at the flow rate once the temperature over here does finally stabilize. So you can see it's starting to slow down at the rate it's decreasing. I don't really know why a lot of the time it seems like there's kind of weird rounding errors that happens with a lot of the different machines in here. If you're running a fission reactor, you'll probably notice that when you're running it, the actual production does not line up perfectly with the heating rate that should happen. But you can see it's going even slower now, and it'll probably settle somewhere around maybe 293, 292 megakelvin. And that's going to produce for us then, since it's a little bit lower, probably around 550,000 millibuckets. But we'll see here, and we'll wait until it actually stops so we can see exactly what we should be getting from this. But we can see over here too that this is slowly settling around 553,000 millibuckets per tick, which is about 5.13 megajoules of power production. Now, obviously, we have a ton of blades in here. This is a relatively large turbine, so that's allowing us to generate a ton of power from each millibucket of steam we put in there. Yours might vary, but that's why you want to make sure that you got as many blades as you can possibly have in here. So, if we take a look at this, it's pretty much stabilized at roughly 292.4 megakelvin, which is awesome. We've got sufficient water in here. You can see that the steam has almost stabilized in here, and we've got maybe 2 million millibuckets of water in here. So we pumped in a little bit extra, but it can't hurt, because if we ever decide to up the rate on this, we can use this excess water to cover for that. So that's pretty much how you set up the water-cooled fusion reactor. It's a lot less scary than setting up water-cooled fission reactors, because there is no risk you blow anything up. It's simply just going to net you way more power for a very little expense. So I would highly advise you, once you have an air-cooled one set up and you've had that running, definitely look into upgrading it into the water cooling. There's really no reason not to, and it looks pretty awesome having this thing run with a massive turbine right behind it. But that's going to be it for today, guys. Hopefully you enjoyed today's episode and get use out of a ton of the power that you're generating, and I will talk to you guys later.
Standing in a glass bowl at the end of a black hole, cold, lost and upside down. Faces swirling past me, all my memories rolling vastly.